You know the feeling. You pull out your phone, you open up the map, and there it is, that little blue dot. You're just trying to find a coffee shop, but then all of a sudden, the dot just jumps across the street. We have all been there. But what is actually going on when that blue dot gets it wrong? Well, today, we're going to find out.
I mean, we completely take it for granted, but getting that dot in the right place is the answer to a ridiculously complicated problem. Your phone has to track signals from satellites thousands of kilometers away, traveling at the literal speed of light, and somehow nail your position down to just a few meters. So where do things go sideways?
To really get a handle on all the errors, we need to follow a single signal on its absolutely epic journey. We're going to start 20,000 kilometers above the Earth, travel all the way through the atmosphere, and end up right inside the electronics sitting in the palm of your hand. And trust me, it is a journey that is packed with obstacles. All right, so our journey begins right at the source, the satellites themselves. You'd think they would be perfect, right? But even up here, orbiting high above us, the very first tiny errors start to creep in before the signal has even begun its trip. Okay, so a satellite's location is predicted in something called an ephemeris file. It's basically its flight plan. But here's the thing. Satellites don't follow their predicted paths perfectly. They have this tiny little wobble in their orbit, and even a deviation of just a couple of meters can throw off the whole calculation down here on Earth by as much as 2.5 meters. Now, as tricky as orbital mechanics are, the single most critical factor for GPS is time. We're talking incredibly, mind-bogglingly precise time. Why? Because your phone figures out its distance from a satellite based on how long the signal took to get to you. And when you're dealing with the speed of light, every single nanosecond counts. And this right here is a tale of two very different clocks. The satellites are carrying atomic clocks that are so accurate, they lose just 1 second every 300,000 years. Your phone, on the other hand, it's got a simple quartz clock. It's good enough for everyday stuff, but it is no match for the insane stability of an atomic clock. And that difference, that's everything. So just how much does that tiny time difference matter? Well, get this. A clock error of just 1/1,000,000th of a second, a single microsecond, creates a 300-meter error in your position. 300 meters! That's like 3 football fields long. This is exactly why getting the timing right is absolutely everything. So the signal leaves the satellite in pretty good shape, all things considered. But now it has to face its biggest challenge yet, Earth's atmosphere. See, it's not empty space. For a tiny radio signal, it's a brutal obstacle course that bends it, slows it down, and introduces some of the single biggest errors in the entire system. The signal has to punch its way through 2 main layers, and each one takes its toll. First up is the ionosphere, this volatile region way, way above us. And if it makes it through that, it then has to navigate the troposphere. And that's the dense, weather-filled air that we live in right down here on the ground. Let's start with the big one. The ionosphere is basically a sea of free electrons and ions, and it's all energized by the sun's radiation. So when our little GPS signal tries to pass through this layer, all those charged particles actually slow it down, which makes the satellite seem farther away than it really is. And because the sun is what powers this whole thing, the effect changes dramatically. During the day, that delay can cause a position error of up to a whopping 60 meters. At night, it drops way down. This makes the ionosphere the single largest natural source of error in the whole system. Period. Okay, so after surviving the ionosphere, the signal hits the troposphere. This is the air we breathe, the part that's full of moisture and pressure changes that we just call weather. This layer also delays the signal, but because it's so much closer to us and easier to measure, its effects are way more predictable and a lot easier to model and correct for. The signal has survived space, it's made it through the atmosphere, but believe it or not, the final few feet of its journey can be the most chaotic of all. Down here on the ground, especially in cities, the signal has to navigate this maze of reflective surfaces, creating what's basically a hall of mirrors effect. This is something called multipath error. See, your phone's antenna is trying to listen for a clean, direct signal straight from the satellite, but it also picks up all these other signals that have bounced off buildings, the ground, or even a nearby car. These reflected signals are delayed, and they just confuse the heck out of your receiver. Think of it like this. It's like trying to have a conversation inside a canyon. Your receiver gets the direct signal, your friend's voice, but it also gets all these delayed, reflected echoes. And all of that extra noise makes it really hard to figure out the correct distance.
So how do engineers even begin to fight this? Well, they're pretty clever. They've developed everything from smart antenna designs that literally filter out the echoes to more advanced software that can actually tell the difference between a real signal and a reflected one.
So after surviving space, the atmosphere, and bouncing off a skyscraper, the signal finally reaches its destination, your phone. But the journey isn't quite over. The receiver itself, the hardware you're holding in your hand, introduces its own final set of tiny little flaws. Remember that less stable quartz clock we talked about? Yep, that's part of it. But there's also tiny amounts of electronic noise from the phone's own circuits, and even physical imperfections in the antenna. At the end of the day, your phone is a compromise. It's built to be affordable and to fit in your pocket, not to be a perfect scientific instrument.
So, we have orbital wobbles, clock drifts, atmospheric delays, urban echoes. It sounds like a complete and total mess. How does GPS even work at all? Well, the answer is that engineers have spent decades learning how to model, predict, and correct for all of this chaos.
They pretty much treat the problem like an accountant would. Each one of these potential errors is like an item in a budget. They add them all up into a single value they call range bias, and then they build these incredibly complex models to subtract that bias out of the final calculation, getting us that much closer to the truth.
But here's a fascinating little plot twist. For a full decade, the single biggest source of error wasn't natural at all. It was intentional. The U.S. military deliberately degraded the public signal in a program called selective availability, intentionally knocking the accuracy down to about 300 meters for security reasons, until it was finally turned off for good in the year 2000.
This table really puts it all together, and what's amazing to see is just how these errors range from a couple of meters for the orbits all the way up to a wildly unpredictable 60 meters from the ionosphere. It's the combination of all these different factors that engineers have to somehow solve for, all at once. And of course, engineers have a name for this whole error budget. They bundle the entire thing into one final number called the User Equivalent Range Error, or UERE. This value represents the total expected error from all sources combined, and the constant goal is to make that number as small as humanly possible. So the fact that your phone can take a signal that's been warped by solar radiation, bounced off a skyscraper, and then processed by a cheap little clock and still place you on the right street, I mean, that is nothing short of a miracle. That jumping blue dot isn't really a failure. It's a tiny glimpse into the colossal chaotic physics that engineers overcome every single second just to get you to that coffee shop.